So we are going to start now with complex numbers chapter. Okay. Some of you would have already started this chapter in school. And those who haven't started it, no worries. We are going to start from scratch. But first, let me give you an overview of what we are going to cover under this chapter of complex numbers. Okay. So under this chapter, we are going to cover, first of all, a general know-how of complex numbers. So we'll talk about a bit of introduction. Okay. Then we'll talk about a representation of complex numbers. A representation of complex numbers. Okay. Post that, we are going to look into operations on complex numbers. Like normally we have, when we learn something, when we know about it, we learn how to operate on them, isn't it? Like vectors, you learn vectors, then you learned how to do dot product, cross product, addition of vectors, right? And why vectors? Let's talk about real numbers itself. When you learned about, let's say you talked about natural numbers you learned in your very young age, right? Then you learned how to add them, subtract them, multiply them, divide them. So once we know what is complex numbers, how they're represented, we learn the operations on complex numbers. Now, various type of operations we'll talk about: addition, subtraction, multiplication, division, finding the nth root of it. Then we'll also talk about the concept of square root, nth root, and log, applying log on complex numbers. So all of those we are going to learn under this particular topic. Finally, we are going to talk about a very, very special concept, which is called the nth root of unity. So it comes from your concept of finding the nth root of a complex number. So this is something which needs a special mention because a lot of questions have been asked on this. So nth root of unity, we'll be talking about that, or you can say nth roots of unity. So we'll talk about this. We'll also talk about a very interesting theorem called the de Moivre's theorem. Okay. Can you teach us logarithm? Logarithm was actually taught to a large extent in the functions chapter, right? We'll take it up again. We'll take it up again in theory of equations. Okay. Not De Morgan. It is de Moivre. Yes, De Morgan's brother. Right? It is pronounced as de Moivre's theorem. Okay. And finally, we'll deal into some miscellaneous concepts, which is basically related to rotation of complex numbers. Okay, or rotation theorems. So this is the coverage of this chapter, complex number. However, if you look at your CBSE curriculum, the NCERT just talks about introduction, representation, and operation. Okay, and a bit of cube root of unity. But they fail to address other two topics, which is your de Moivre's theorem and your rotation theorem, which we'll be covering in our concept. Now, many people ask me how many classes normally will it take to cover up this chapter. We will take around 2 full-length classes to cover it. So minimum of 6.5 hours duration will be required for this topic. Okay. So today is 1 hour lecture, and apart from it, we'll need, I think, 5.5 hours more to finish up this up. Okay. So let's get started with complex numbers. Right now, complex number, what was the need for such a number to come? Right now, if you start with the evolution of numbers, you would realize that the primitive man, right, the ancient man, he only needed natural numbers, right? Because he either needed to see how many hunting he had made or how many fruits he has gathered during the day. Right, so let's say if he has killed 5 animals, so he just need 5 as a natural number, right? If he has gathered, let's say 100 fruits, so he just needed 100 as a natural number. So our primitive man only needed natural numbers to get all his job done, right? And then they started the concept of lending, right, giving and taking. Right, so let's say if I give you 5 mangoes, and I take the 5 mangoes back from you, how many mangoes will you be left with? Now there is no natural number to explain that. So 5 minus 5 gives you a 0, but 0 is not a natural number. So then man had to invent 0 along with natural numbers, which made his basically quest of numbers whole or complete. And that is why incorrectly they said these are all whole numbers. Whole means because they thought their quest for numbers is over. They don't need any other number. So once 0 was included, they thought that all the numbers they know, whole, that is everything they know. But then started business engagements, right, where borrowing and lending used to take place. So if I give you 5 mangoes and I ask you 7, then what do? You have to take 2 from somebody to give me 7, isn't it? So how do you show that borrowing of 2 mangoes? So now that we know that, we use -2 for it, isn't it? But that time -2 was not known. It was only till whole numbers. So man had to get into negative numbers, and as a result, he got integers, isn't it? So integers are basically, let me just make a set out of it. So basically within integers, there are whole numbers, okay? And within whole numbers, there are natural numbers, right? So this is how the things were moving on so far. So natural number, and if you include a whole number here, sorry, include a 0 here, it became a whole number. And this whole thing was included in integers, where apart from whole numbers, we also have negative integers coming into picture. Okay. Now, slowly man started doing farming, right? We started engaging ourselves into farms, isn't it? So let us say I have a farm, okay? I have a farm whose, let's say, dimension is, let's say 10 by 10 meters, or you can say 100 meters square dimension. Okay, so this is a 100 meters square farm. Okay, and let us say I have 3 children and I want to divide my farm equally among them. Correct? So what do? How much land do you give to each one of them? How much land do you give to each one of them? 100 by 3, isn't it? But by that time, 100 by 3 was not known. We only knew integers. So man had to come up with rational numbers then. So he had to start with rational numbers, where he could basically take care of such nitty-gritties in division of objects, isn't it? So now it came to rational numbers, which he started calling as Q, isn't it? Now let's say the very same land that I have over here, I want to divide it from the diagonal position. Let's say I want to put a mesh here in the diagonal position, right? So this is a square piece of land of dimension 10 by 10 meters, and I want to put a mesh in the diagonal position. Can you tell me what should be the length of this diagonal? What should be the length of this diagonal? 10 root 2. That is what you know right now. But that time, when it was only rational number, root 2 was nowhere into the picture, isn't it? So man needed irrational numbers then. So it is the requirement of man that he started coming up with these, new inventions, right, of numbers. So let's now talk about a bigger set now, which is your irrational numbers. Okay, so there were irrational numbers, I will call it as, and they were rational numbers, and together he called them as real numbers, right? So real numbers include both your rational and irrational numbers, isn't it? Now, when the scientific age came, he started solving equations. And then he fumbled upon a very interesting equation, which is x squared plus 1 equal to 0. Right? And he realized that there is no answer x which is real, which is going to satisfy this. Now that we know the answer, now we know the answer is I, right? But that time, when basically complex number was not into picture, people were not able to imagine any real number whose square plus 1 will give you a 0. Of course, Cardan was the first person who could figure it out, right? And when Cardan figured it out, he basically started calling them as not imaginary numbers. He actually called it as the latent numbers. Later on, there was a lot of mathematician who started using this, Okay, and they gave a word imaginary to it. Okay, now see, the complex numbers that you are going to study right now, it's actually a bigger set of real numbers themselves, right? So all real numbers are actually complex numbers also. But apart from real, you have imaginary numbers as well, right? So there could be imaginary numbers, there could be real numbers, and there could be a mix and match. That is what we call the entire set as a complex number set. Okay, is it clear? So what was the need for a complex number? This story is clear to everybody, right? Now let us talk about the complex number itself. So when you talk about complex number, understand here that complex number is a two-dimensional number, and we normally use the alphabet Z to represent it. Okay, so when we write a complex number, we write it as A plus IB. Now what is this I? I is something which I already briefly talked about in the previous slide. So I that we know now is the under root of -1. But let us understand what is the need of this I. Okay. Yes. Okay. Now small z. This is not a capital Z Omkar. It's a small z. Capital Z is for, yeah, capital Z is for integer. Okay. Now this I basically acts like a unit for imaginary numbers. Okay. Just like the number 1 acts like a unit for real numbers. Now what is the meaning of unit? See, let's say I want to say I want 5 mangoes and 3 oranges, right? So 5 is the amount and mango is the type of fruit that I need, isn't it? So without that, without the combination of these two, I will not be able to convey the idea that I need 5 mangoes, isn't it? Similarly, 3 oranges, 3 is the amount and O is the type of fruit which I need, right? So if I want a collection of 5 mangoes and 3 oranges, I have to speak this out: 5 mangoes and 3 oranges, or plus 3 oranges, isn't it? In the same way, when you want to write a vector, let's say you have already done a bit of vectors in physics. So let's say I want to write 3i plus, or let's say 5i plus 3j. So what are you trying to say here? You're trying to say here that there is a vector, which basically is spanning 5 units along the positive x direction and 3 units along the positive y direction, right? That is how you call this vector as 3i plus 5j. So what is this I cap and j cap there for? Why don't we just write 5 plus 3? Sir, if I write 5 plus 3, it will become an 8. So that will not be able to convey the idea that I want people to understand. So I want people to understand that there is a vector which moves 5 units along the positive x-axis and 3 units along the positive y-axis, right? So I have to put some unit there to make that identification. So this I cap acts like a unit vector for you along the positive x direction, and j cap acts like a unit vector for you along the positive y direction. In the same way, when you want to write a complex number, it will have a real part to it. This is called the real part of the complex number. And it will have an imaginary part to it. So complex number is a two-dimensional number, where one dimension is a real dimension and other dimension is an imaginary dimension, right? Now, many people ask me, sir, why do we need a real and imaginary dimension? See, later on, I come from an electrical background. I've done my BTech in electrical engineering from IIT Kharagpur. So we had to study something related to power, right? And I was very surprised when my professor told me power is sometimes real and sometimes imaginary. In fact, in capacitors and inductors, the power saved is an imaginary power. Okay. So power itself is a complex number, right? It could have a real part and an imaginary part. Real part is what your wattmeter can measure. Imaginary part, your wattmeter cannot measure. Okay. So many things in your future, you would realize that they will have a real and imaginary dimension to it. Okay. So many cases, like, let me put this as a very interesting fact to you. All of you have seen circles, right? Okay. Let's say I have these two circles, circle A and B. Let me call them as circle A and B. How many common tangents they have? Can anybody tell me that? How many common tangents they have? Okay, two like this, they are called direct tangents, and two like this, they are called transverse tangents, isn't it? Yes or no? So a circle here in this case has got four common tangents, and all the four tangents here are real, right? Because you can see them, correct? So here all the four tangents are real because you can see them, right? Now the very same circle, if I bring them closer, let's say A and B now touch each other. Okay, tell me how many common tangents there you will have. How many common tangents you will have? Okay, let's count. Let's count. You will have two direct here. Oh, sorry. You will have two direct here. Okay, right? And you will have two real and coincident tangents here. So what will happen? These two blue lines that you see, when the circles start coming closer and closer, these two lines will start becoming like this. Look at my camera. They'll start coming and they'll become overlapping, right? So you still have four tangents, okay, and all of them are real, but two of them are coincident. But two tangents here are coincident. That means they are one over the other. And that's the reason why you are seeing them as a single line, right? So math says that you still have four common tangents, but two of them are coincident. Okay. Okay. Now let me continue the story. Very interesting story. A lot of lessons to be learned from this. If let's say these two circles barge inside one another, then how many common tangents will they have? Okay, now the answer here is there is still four tangents, but since you can see two, you are saying two, but there are two real ones and two imaginary now. So that the tangents which you are not able to see, they are now imaginary tangents, right? So what happened is that this tangent, blue tangent, now went to an imaginary space. It went to an imaginary domain. It is no more real now. Okay, so mathematics says there are still four tangents. Two of them are real and two of them are imaginary. I know this will be, blowing off your mind, right? You never had thought about it. Okay, now let us say one circle goes inside the other but touches it internally. Then how many common tangents? How many common tangents? This time you'll be careful in your answer. There will be four tangents. Two real and coincident, two real and coincident, and two imaginary. So the coincident ones appear to be as if there are one line, but there are actually two coincident lines. So what happens is, as this guy keeps on moving inside, these two lines from this position, they start coming as a single line. Okay. Okay, now let me take the last case. Yeah, what if one circle goes completely between inside the other? There will still be four tangents, but this time all the four tangents will be imaginary. Yes. Okay, so there are many things which maths basically explains as imaginary. Okay, but I know it is very useful in your solving of equations also. There are many roots which you will not see them cutting, right? But they are still the roots of it. So we'll talk about them in the theory of equations chapter. Okay, anyways, coming back to this. So why do we need this I? So this I is acting like a unit for imaginary number. So if I have to say I want a number of unit 1 and b number of the imaginary, then 1 and I basically act like their units. Okay. So when you write a complex number as 3 plus 4i or 3 plus i4, doesn't make a difference. Both the notations are treated to be the same. What it actually means? It means that this complex number is formed by taking 3 units of 1, 1, 1, 1, and 4 units of an imaginary quantity or imaginary unit I. Okay, so 3 plus 4i basically is this complex number formed by 3 real parts. So its real part is 3. Okay, and 4 will be the imaginary part. Please note, 4 is the imaginary part, not 4i. I is just acting like a unit. Okay, so when you write a complex number a plus ib, the real part of that complex number represented as re of z is your a, and imaginary part of that complex number is your b. Please make a note of this. Okay, so tell me, simple question, answer this simple question. If I write a complex number 2 minus 3i, what is the real part of this complex number? Write it down on the chat box. 2. What is the imaginary part of this complex number? Minus 3. Don't say 3i or minus 3i. It is just minus 3. Got it? Any questions? Okay. So when you are framing a complex number, you are framing it like this: real part plus I times imaginary part. Understand this. So this is how we frame a complex number. Okay. So if a number is purely real, so if z is purely real, then it implies that imaginary part is 0. Okay. And if z is purely imaginary, then the real part is 0. Okay. Example of this would be a number like 3. So if you write a complex number 3 is a purely real number, so its imaginary part is 0. Okay. Example of a purely imaginary number would be something like 2i. That's a purely imaginary number. Okay. Any questions? Now we are not going to leave this I behind. We are going to talk about I. I is very important for us. So what is this I? First of all, I, there are different names people give it. Some people call it as IOTA, right? Some people call it as I of that imaginary thing. Okay. So what is this number actually? So this number, we already know, it's actually a unit of imaginary number which has been chosen to be under root of -1. Okay. This is what we call as I in mathematics. Okay. Now this I has lot of properties. What are the properties? Let's try to figure it out. If you square this I, what do you get? What happens when you square both sides? You get -1, right? So for the first time, you're seeing that something square is giving you a negative answer, right? That is how imaginary numbers behave. Okay. So square of any real number will never give you a negative answer, but square of imaginary numbers can give you a negative answer, right? If you do I cube, what happens? Can I say I can write it as I square into I, which is back to -1 into I, which is minus I? Yes or no? And I to the power 4 will be what? I to the power 4. You'll say, sir, simple. I square, which is -1 square. That will give you a 1. Correct? And if you see, there is a cycle that is followed by I. So if you do I to the power 5, it will be back to I again. Isn't it? Because I to the power 5 is what? I to the power 5 is I to the power 4 into I, and I to the power 4 is already 1. Similarly, I to the power 6 will be back to -1. See, now compare. This is back to I. This is back to -1. Right? So what will be I to the power 7? I to the power 7. That will be back to -I. I to the power 8. 1 again. Again I to the power 9. Back to I. I to the power 10. -1. I to the power 11. -I. I to the power 12. Back to 1. So this is how it follows a cyclic nature. Okay, it has got a cyclic nature. So after every change of power of 4, it will come back to the previous value. Okay. So in order to generalizing this, can I say I to the power any 4n power, n being an integer, will bring you back to 1. I to the power any 4n plus 1 power, of course, again, n is an integer, will bring you back to I to the power 4n plus 2 will bring you to minus 1, and I to the power 4n plus 3 will bring you to minus I. So this is something which you need to note down. Very, very interesting property. Some questions can be framed based on basis of this property as well. Okay, so far so good. Story of I, you're able to understand? Okay. Now I has a very interesting property as well. This is property number 1. Another property that I shows is, if you take any consecutive powers on I, let's say I to the power p, I to the power p plus 1, I to the power p plus 2, I to the power p plus 3, and add them, it will always give you a 0. Okay, it will always give you a 0, right? P could be any real number here. Why does it happen? Very simple. If I take I to the power p common, it will give me 1 plus I square plus I cube, isn't it? And I square is minus 1, I cube is minus I again. So they will each cancel each other out, giving you a 0. Okay, so this is very important. Sum of 4 consecutive powers on I, consecutive means gap of 1, of course, consecutive powers on I will always be a 0. So these two properties are very, very important. Questions have been framed on these properties in the past. Is it fine? Any questions? Please note it down and let me know if you have any questions. Okay, let's take a few questions on I itself, and then we'll move on to representation of complex numbers. So let's talk with I for some time. Oh, sorry, we are already into complex numbers chapter. So let me go back. Okay. Let me begin with this property. This question. So all of you know summation symbol, right? Summation symbol means adding them. So if you start putting R as -3, -4, -3, -2, -1, 0, 1, 2, 3, all the way till you go to 1003 and put those R values on I and add them, what is the value going to be? That means the question setter is asking you I to the power -3, I to the power -2, I to the power -1, I to the power 0, I to the power 1, I to the power 2, all the way till you go till I to the power 1003. What is the result going to be? Options are given to you. So I'm going to put the poll on for you all. So please give your response on the poll. I'll put it on the poll, Omkar. Yeah. Very good. 50% of the people have responded. I can give you 1 more minute here. Okay, time up. So I'm ending the poll now. Those who want to vote now, last 5 seconds. 5, 4, 3, 2, 1, and go. Okay. If you see the response, you can see the confusion in the response. B, C, D, almost same number of votes. What does it show? Terrible confusion. Confusion, confusion, confusion. Okay, let's clarify that confusion. Okay. See it. Let me write few more. If you see the last property, what did we discuss? We discussed that if you take 4 consecutive powers of I, they will add up to give you 0, right? So can I say I to the power minus 3, minus 2, minus 1, 0 will add up to give you a 0. This will also give you a 0. Can I say if I continue making it till I to the power 1000, this will be 0 only, because from 1 to 1000 there are 1000, and you can make 250, you can say a group of 4s, right? So they will all be 0. So what will I be left with? I'll be left with I to the power 1001, I to the power 1002, and I to the power 1003. So these 3 will be left. Now 1001 is which type of a number? This is 4n plus 1 type of a number. So this will give you an I only, isn't it? So what will be this now? I to the power 1002. That will be I square, which is actually minus 1, isn't it? And this is what? This is 4n plus 3 type of a number. So this will give me a minus I, isn't it? So since this is 4n plus 2 number, it will be minus 1. Since this is 4n plus 3 type of a number, it will be minus I. So they will cancel each other, giving you a minus 1. Okay. So option number B is right. So B got marginally 1 vote extra. So because of that, right? Thankfully, Janta gave a right response. So B is the right option. Is this fine? Any problem, any concerns here? Any problem, any concerns here? Anybody? Can I take another one? Let's take another one. Okay, so this is again a summation question. Now this term is I to the power 2n plus 1 factorial. Now how many of you don't know what's a factorial? This is a symbol of factorial. Is there anybody who doesn't know what's a factorial? No? Okay, so what is factorial of a number? Factorial of a number is a product from 1 till you reach that number. For example, if I say 4 factorial, right? It is represented as a 4 with a exclamation symbol. It means product from 1 to you reach 4. So that is 24. Okay. So here in my question, I have I raised to the power 2n plus 1 factorial, and n is going from 0 to 50. So what is this going to simplify to is what the question setter wants to know. Okay. So basically you're trying to sum up I to the power. If I put a 0, I get 1 factorial. If I put a 1, I get a 3 factorial. And this continues till I reach I to the power 101 factorial. What is this sum going to be? So again, I'm putting the poll on. Please give me a response on the poll. Yes, Omkar, we are going to study this under permutation combination chapter officially. Yes, correct. 1 minute gone. I can see only 3 people responding, so I'll definitely give you more time. Come on, guys. This is not a difficult question. I hope you are not sitting and calculating each of these factorials and trying to solve it. That's going to take you lot of time. Okay, 1 more minute I can give you because it's already 2 minutes and this is worth only 30 seconds, not more than that. Okay, I'm starting the countdown. Those who want to vote on the poll, please do so in the count of 5. 5, 4, 3, 2, 1, go. Okay, 12 of you, in fact 13 of you have responded, and out of 13 of you, 7 of you say option number C. Okay, let's check. See guys, understand this fact. 1 factorial means 1, right? 2 factorial is 1 into 2. 3 factorial is 1 into 2 into 3. But the moment you do 4 factorial, you basically end up introducing the 4, right? So this becomes a multiple of 4 for sure, right? And even if you do 5 factorial, you have that 4 inside that, right? So this is still a multiple of 4. So what do you realize here? You realize here that after 5 factorial, all these numbers that you are seeing here, they are all multiples of 4. Correct? Because while writing their factorial, you would have definitely written a 4 in the product, isn't it? So they all become multiples of 4. Isn't it? Isn't it? So what will happen? These all guys will start giving you 1, 1, 1 each. Dot, dot, dot. Okay. Yes or no? Right? So let's try to summarize what is going to happen here. So I to the power 1 factorial, that is I to the power 1 only. I to the power 3 factorial, which means I to the power 6. And rest all of them will give you 1, 1, 1, 1, 1. Correct? No? Yes or no? So out of 51 terms, 2 of these will be these and remaining 49 ones you will get. Right? Yes or no? So in short, your answer will be I to the power 6 will be -1 plus 48. Correct? So altogether, sorry, 49, not 48, 49. Yeah, altogether your answer will become 48 plus I. Is there any option which says it? Yes, option number C is right. Is this fine? Any questions? Any questions? Any concerns? Okay. Now I'll ask you a question which is very, very interesting. Give me a second. I think, did I lose that question? Are you? No, it's here. It's here. Yeah. Very interesting question. So in this question, we have got 4 statements. If you see, there are 4 statements in this question: statement 1, statement 2, statement 3, and statement 4. Okay. Statement 1 says, I can write -6 as 2i into 3i, right? Which is as good as saying I can write 2i is under root of -4, 3i is under root of -9. S2 says I can write this as this. S3 says I can write this as this. And S4 says I can write root 36 as 6. You have to identify which statement is an incorrect one. Which statement is an incorrect one? Incorrect one. Okay. I'm relaunching the poll. I'm relaunching the poll. Okay, so Krishnendu, what's the response? What answer did you pick up? Okay. Let's see what is the actual answer. So we'll see whether your answer is right or not. Guys, 20 more seconds. Anybody wants to vote in the next 20 seconds, please do so. Okay, 5, 4, 3, 2, 1, and go. Okay. Now, many people have voted for option number B. B for Bangalore. Okay. Then second highest vote has gone to A. Let's check. So let's see whether B is right or not. See, root of -4. Of course, root of -4 is 2i. Okay. But even before we say this, please understand this fact. Very, very important. When we say under root of AB is under root of A into under root of B. Okay. This particular identity that you have been using since your childhood, this identity works when at least one of A or B is greater than equal to 0. Right? So when you're using it here, it is fine to use it. Right? But if both of them are negative, that means if both of them are negative, A and B both are negative, then the same identity will actually become negative AB is under root A under root B. Okay. This is something which many people do not know. Please note this down. And that is what is being tested in this question. So in this question, under root of -4 is 2i, under root of -9 is 3i, correct? And when you multiply these two, right, it definitely gives you under root of -4 into -9, but with a negative sign, which is under root negative under root 36, which is -6. And that is what we know as 2i into 3i. Correct? So this statement S1 is correct statement. This statement is a correct statement. Okay. But statement number 2, this is a wrong statement. Because you cannot apply this property here. This property will not work. Which property will work? This property will work now. Right? It is because both your A and B are negatives. So they will each contribute to an I each. Isn't it? So this will give you 2i, this will give you 3i. So this should be your 6i square. And what is 6i square? 6i square is -6. But what will this give you? This will give you root 36, which we have learned is 6. So they are definitely not equal. Okay. So statement number 2 is wrong. Statement number 3 is again right. This is under root of 4, under root 9 is 36. 36 is under root 36. Nothing wrong about it. S4 is also right because we have already learned it earlier as well. So option number B is the incorrect option here because S2 is a wrong statement. Okay. So Krishnendu, sorry, what you thought is not the case. Okay. So B, the learning here from this exercise is this, that under root of A, B cannot be written as under root A, under root B, and vice versa when both of them are negative. So for this formula to be applicable, at least one of them should be greater than or equal to 0. Right? Either A or B or both of them. At least one of them should be greater than or equal to 0. Then only this formula works. If both of them are negative, then unfortunately you'll end up getting negative because these guys will contribute I each. But this guy will be positive. Isn't it? So it has to be something I square, which will lead to a negative answer. Okay. So that is how this particular concept becomes important. Okay. Now please note all your identities, your that is A plus B whole square, etc. They will all work on complex numbers also. For example, if I want to square it, I can always do A square. I can do IB square. I can do 2A into IB. Okay, but when you are expanding it, be careful. This will lead to A square. Here you will get I square B square. I square B square is minus B square. And this will be I times 2AB. Okay, so all your identities that you have learned, in fact, I'll write minus also. So even if you do square of this, you end up getting A square, IB square minus 2A minus, sorry, I've already taken a minus now, so I'll not take here. So on simplification, this also will give you A square minus B square minus I to AB. Okay. Similarly, if you want to do A plus IB whole cube, same formula that you have studied in your junior classes, cube of this, then 3A square IB, then 3A IB square, then IB whole cube. So this will all be applicable. This will become 3A I square B square. I square is -1, so that will become minus 3AB square. And this will become I cube B cube. I cube B cube is minus IB cube. Okay. So you can collect all the real terms together. It's a good habit to write real terms at one place and imaginary terms at one place. Okay. So this can continue on and on. So all your regular identities you can use even on a complex number like this. Right. So based on this, there is a small question that we'll take up. Let me put a question here itself. Yeah. Yeah. If x is -5 plus 2 under root -4, Find the value of this entire expression. Okay, first of all of you realize that your x is -5 plus 2 and root of -4 is 2i, right? Yes or no? So your x is -5 plus 4i or i4, whatever you want to write it. It is up to you. This notation is also accepted. This notation is also accepted. It is up to you. Okay. Now what next? What next? Now, how many of you here, tell me very, frankly, how many of you are actually sitting and finding power of 4, power of q, power of 2 on this complex number and putting it here? I know people would be tricked here. People are going to get tricked here, right? Trust me, guys, you don't need that. See, let's have a smarter way to solve this question. If you are going to do that, mind you, it's going to take you 7 to 8 minutes to solve this simple question. Okay. So see the process. Now I'll show you something very interesting. You can use it for similar questions. Since you know x is -5 plus 4i, take this -5 to the other side. Okay. Square both the sides. Square both the sides. So when you square this, it becomes x square plus 10x plus 25. This becomes -16, isn't it? So this gives you x square plus 10x plus 41 equal to 0. Correct? Right? Now what do? You divide this term. You divide this term x to the power 4 9x cube plus 35x square minus x plus 4 by this term x square plus 10x plus 41. Okay, so let us divide it. Let's do our long division method. So since there is an x to the power 4, you'll have to multiply with x square first. So you'll have something like this. Okay, subtract it. So subtract will give you minus x cube minus 6x square minus x plus 4. Then put a minus x. I'll tell you the reason why I'm doing it. Some of you would be wondering, why is sir doing this all long division here? Don't worry, I'll explain you in some time. So this is going to be 4x square. This will be 40x plus 4. Then put a 4 here. You'll end up getting 4x square plus 40x plus 164, right? So on subtraction, this gives you minus 160, right? Now, what do I mean to say by doing this operation? This operation tells you that this expression that you have, let's call it as the dividend. Dividend can be written as divisor times quotient plus remainder, right? Isn't it? Now, the moment you put your x as -5 plus 4i here, that means you're putting -5 plus 4i here also. But this guy will become a 0, no? Because you already know that this is 0 here. So what it will do, it will make this whole thing go 0. And as a result, your answer will be minus 160. This is your answer to that question. Done. Problem solved. No need to sit and do power of 4, power of q, power of 2. You will waste a lot of your time. Just do this. Plain and simple. Of course, long division, you don't make any mistake. Rest, everything is clear. Isn't it? So 0 into anything, whatever it came, will be make it 0. So only minus 160 will be left off. So that will become your answer. So this problem is an under 2-minute question. Should not take more than 2 minutes. Yeah, many people tried factorizing, etc., and it did not work. Okay. So please note the process. The process is very important. You can use it for similar type of question. Okay. Any questions here? All right. So with this, we now end the story of I, and now we move on to our representation of complex numbers. Representation of complex numbers. Now, complex number is represented in 3 ways. One is called the point form. Okay. So in point form, you represent a complex number as a plus ib. Okay. I'll tell you why we call it as a point form. Another form is the trigonometric form, also called as vector form. And more popularly, it is actually called the polar form, which is what they may be calling in your school also, polar form, right? So in polar form, you represent a complex number as r cos theta plus I sin theta. I will discuss about this r and theta, everything with you, not to worry. I'm just showing you the way to write a complex number. So a complex number can also be written like this. Many a times, if you see international books, they will write it as r cis theta also. Okay. C for cos, I is your iota, and S for sine. So they write it in a simpler form. This is an abbreviated form, short form of r times cos theta plus I sin theta. So they may also write it as r cis theta. Okay. Don't worry about what is this r and theta as of now. I'll explain everything to you, not to worry. Now, another form to represent a complex number is called the Euler form or Euler's form, written as Euler but pronounced as Euler. Euler, the famous Swiss mathematician, you would have definitely heard of his name before. So Euler figured out that you can actually write a complex number as r e to the power I theta. Again, don't worry about all this. We'll be talking about all of them in much more detail. Okay, Euler's number, Euler constant. Euler has got more than 90 references in the field of mathematics. Okay, so Euler was a god of a mathematician. Okay, anyways. So let's talk about the point form first. What is this point form? Okay, so we'll talk a little bit more about point form. Maybe I will not be able to talk everything in the remaining 15 minutes. I'll have to discuss more. See, when you write a complex number as a plus ib, okay, you can actually symbolize this on a plane, okay, which we call as the Argand plane, whose x-axis, normally we don't call this as x-axis. Now this is your real z-axis and this is your imaginary z-axis. Okay, note down, the only number which is both real and imaginary at the same time is 0. Okay, so 0 lies in the intersection of real z-axis and imaginary z-axis. Okay, so this plane is called the Argand plane. Okay, not the Cartesian plane. Cartesian plane is a real plane. This is not a real plane. This is a plane which is made up of what is that in Euler form? Omkar, didn't I say I'll explain everything to you as of now? Hold on. R, E, I, everything I'll explain it to you, not to worry. Okay, just hold on. because slowly we'll unfold things. Okay. This plane is also called as the Gaussian plane also. Some books will also call it as the Gaussian plane also, after Carl Friedrich Gauss. Okay. So on a Argand plane, you can actually represent A plus IB like a point, right? So this A now will be your real part and B is now your imaginary part. So as you can represent a complex number as a point on the Argand plane, the same reason makes the name here very obvious, point form. Okay. So let's say if I want to represent 3 plus 4i or 3 plus i4, how would I represent it? I will represent it like a point here, 3 comma 4. Okay. So basically what point form is allowing, it is allowing complex number to be treated like points or coordinates. And thanks to this point form that we can now apply all our coordinate geometry fundamentals even to complex number. Okay. So complex number, you would realize in some time, is a very diverse concept. It would use your coordinate geometry fundamentals. It will use your trigonometry fundamentals. It will even use your vector fundamentals, right? So many people find this chapter easy and at the same time difficult because there are so many, I can say, versions of complex number. So in a complex number can be treated like a coordinate. It can be treated like a position vector, right? So it sometimes makes your life easy also, sometimes it makes your life difficult also, right? So it is all dependent upon how deeply you understand this complex number. Okay. So because you can write complex number like a point, this is what we call as a point form. Now, there are two terms that we need to understand here very closely: modulus and argument. We'll talk about modulus first. Okay. So what is modulus of a complex number? What is modulus of a complex number? By the way, symbol for that is Z written within parallel lines. Okay. Now, what is modulus of a complex number? Now, note this down. Modulus of a complex number, Z, which is A plus IB, okay, is the distance of Z on the Argand plane from the complex number 0. Okay. So if I ask you what is modulus of A plus IB, so what are you going to do? You are going to just figure out what is this distance from A to this point, right? So use your coordinate geometry fundamentals. So what's the distance of 0, 0 from A, B? How do you find that? 0, 0 from A, B. You say A minus 0 square, B minus 0 square, correct? And that's the modulus of the complex number. Okay. And this is what we used to call as R. This is also called as R. Also known as R. Right? So somebody was asking me a little while ago, what's that R and all? This R is your modulus of that complex number. And what does modulus geometrically represent? It geometrically represents the distance of that complex number point A, B from 0, 0. Clear? So can modulus ever be negative? Never, because it represents distance. Absolutely. Now, if let's say this Z was purely real, that means if your complex number, note this down, if your complex number is purely real, then mod of that complex number is nothing but mod of A itself, right? Hence the symbol that we use is the same as what we use in our actual mod function when we were studying functions. So same symbol is basically used. Okay. Is it fine? Any questions? Okay. If your Z is a purely imaginary number, right? If it is purely imaginary number, I'll write IMG for imaginary, then note that mod Z will be mod of B. Okay. For example, if somebody says, what is the modulus of, in fact, we'll take many questions here. What is the modulus of this complex number? What is the modulus of this? -3 modulus? Or what is the modulus of this number -3? You say 3 only, right? If somebody says -5i, what is the modulus? 5. Exactly. Is it fine? Any questions? Okay. So now I'll give you few questions to figure out the modulus. Find the modulus of the following complex numbers. Oh, I'm so sorry. Sorry for turning the page back. Modulus of I means 1i. So it will be 1. Got it, Raj? Done, copied? Okay, let's take questions. Okay. So first question, what's the modulus of -10? What is the modulus of 4i? I'm giving you simple question to begin with. What is the modulus of -12 plus I root 3 by 2? What is the modulus of I minus 4? Okay. And fifth one, very simple question. I mean, different question. Represent on a graph, or you can say represent on the Argand plane. That would be a right word to use. Represent on Argand plane all Z that satisfy mod Z is equal to 2. Good. People are already answering 1, 2, 3, and 4. So 5 also. I mean, 5 you will not be able to answer, but you can just write down how would that representation actually look like. Shreya, are you sure of the third and the fourth? And Aditya, are you sure of your fourth answer? Very good, Anika. Very good, Arthur. Nice to hear that fifth answer from you. Okay, should we discuss? Should we discuss, or you want more time? Anybody wants more time? One second. Okay, fine. Shall we? Okay. The first answer here, mod Z will be 10. Any problem with this? Okay. It's as good as saying -10 square plus 0 square, because you can write this as 0i under root, right? Which is under root of 100. Under root of 100 is 10 only. This will be 4. It is as good as writing under root of 0 square plus 4 square, because you can write it as 0 plus 4i. So this square, this square. Now don't square I along with it. There are people who make this mistake. They will do full a square and ib square. No, don't do that. You don't include your I in that squaring part. Only a square, b square. Don't put your I inside. So root 16, that's your 4 itself. Similarly, this will be what? Under root of minus half square and just root 3 by 2 square. Don't put an I. So that will become 1/4 plus 3 by 4. That's nothing but under root 1. That is 1 itself. Okay. This is going to be under root of minus 4 square plus 1 square, because your imaginary part is 1 here. So that will be root 17. Okay. Now the last question which I asked you, I wanted to test your geometrical understanding about mod. So here you are trying to show all such points whose modulus is 2. Correct? And what does modulus represent? Modulus represents distance of the point from origin, isn't it? So all such points whose distance from origin is 2, how will they be located? How will they be located? Take a hint from what geometrical figure I am selecting. No. Right. So it will represent a circle whose radius is 2. So this is basically an equation of a circle in complex plane. Okay. Because all the points that you take here, they will all be at a distance of 2, 2, 2 from the center. Isn't it? So they will all be located at a distance of 2. Clear? Okay. We'll talk more about these stuffs as the chapter progresses. But please mind you here that JEE is looking out for these understandings. What you see in your NCERT, that is nowhere close to what JEE will ask you in complex numbers. JEE has a different trajectory altogether. Why not a right angle triangle? Why should it be a right angle triangle when the definition here says the distance of Z from origin is 2? This is the only figure where any point you take on this is distance from the origin is 2. Why should it be a right angle triangle? Tell me. If you make a right angle triangle, Raj, how will you make that? Let's say you make a right angle triangle like this. What does it mean? It means the distance of this is 2. Distance of this also is 2. Distance of this also is 2. Does it mean like this? No, right? Okay. All right. So we'll stop here. Next class, we are going to talk more about argument part. Okay. So over and out from my side for now. Thank you. Bye-bye. Take care.